Hello, everyone. My name is James, and I will be your host for today's webinar. Welcome to Secure and Reliable Networking for Smart Grids. Joining us today is Moxa's Senior Industry Marketing Manager, Kuru Kuruvilla. Kuru holds a master's in electric power engineering and has experience in power generation, renewables integration, and distribution grids. He's obtained multiple U.S. patents related to power system operation and control, and has held various positions in design engineering, application engineering, product management, and marketing. A couple of housekeeping items before we jump into our presentation. The webinar is 45 minutes, including time for questions at the end. If you would like to submit questions, please use the Q&A function. You'll also see the occasional poll question pop up on your screen, so we encourage you to participate in those. The recording will be shared so you can go back and watch the webinar on demand. There will be a survey at the end of the webinar, and we appreciate your feedback on the presentation. And with that in mind, I'll pass it off to Kuru to kick off our webinar. Kuru.
Thank you, James. Good morning, good afternoon. So today we are going to cover a few topics related to electric utilities and how communications is a key aspect of optimizing the electric power grid. We'll talk about some of the trends and challenges, the importance of resiliency and redundancy in communication, the critical aspect of cybersecurity, and we'll kind of end with what to look for in a partner as you go forward in this journey. So I thought I'll start with some recent headlines that talk about that concern electric power grids. So the first one I found, it said power grid is the largest machine in the world. It's a great engineering achievement. Another one talked about the U.S. urgently needs to expand the grid. There's the other one I found, which was more on the fact that the grid is so valuable that the price of or modernizing should not be a limitation. And then the last one I saw had to do with security, right? So if you look at all these four headlines, you kind of find that there is a lot of pride in what has been engineered over the last many decades or a century. There is obviously an understanding that the grid needs to grow and that there is going to be a cost associated with it, but that cost is well worth it. And then last, there is obviously legitimate concern on how do we make sure that we operate it in a secure manner. So before we kind of talk about some of the challenges, I just wanted to get a feel from the audience here. What do you think is the biggest challenge that electric utilities face today? So I'll give a minute for all of you to kind of take a look at it, give your thoughts and feedback. Okay, very interesting. I mean, it's there is all the different areas are kind of covered, but I see cybersecurity is kind of top of mind, and then integrating energy resources, reliability, and the increase in EV charging. So now we'll close the poll and kind of look at just from a perspective of the electric utilities, right? If you ask them this question, what are some of the feedbacks that you get? And this is from a survey that Black & Veatch did in the last year or so. And if you look at it, I mean, all the topics you all thought were important. They're all in the kind of the top 5 list. But the number one thing that kind of came out was improving reliability, right? Is kind of perceived as the number one need of the hour. Obviously, cybersecurity, resilience, closely tied. Is it's kind of I would say close second, as is the integration of the distributed energy resources. So I thought we'd kind of start this discussion, just, kind of laying out, some of these kind of detailing, right? Some of these challenges that we are seeing on the grid. Improving grid reliability, right? So essentially, that means, you want to minimize the downtime, and then you want to, lower your operational expenses in terms of having to go and, fix, right, things that may have gone wrong. What you see in the graphs are, some of the metrics that are typically used to track reliability, right? So first one, on the left is what you call SAIDI, which is, the number of times on average, right? You have outages. Then you kind of talk about what is the duration of those outages, how long does each of the outage last, and then on the bottom you can see something called Mayfi, which is kind of the momentary outages, right? Versus something that is sustained for a long period of time. And what you see in all these graphs is that, if you go back in time over the decades, you would see that, some of these numbers have improved. But in the last 10 years or so, they have been pretty stable, right? So the improvement has kind of plateaued. And again, it means to the utility loss of revenue for sure, in some cases, regulatory penalties, customer satisfaction scores. So that's kind of the first thing to kind of think about, right? Why is reliability important, for the grid? Another topic that is, top of mind is, reducing the line losses. So there is, a lot of losses that happen in transmitting and distributing energy. If you look in the US, it's roughly in the 5%, meaning that, only 95% of the energy that is generated ultimately reaches the customer and hence it's billable, right? And what you see on the right side is, just the price of electricity, right? So every kilowatt hour that is not sent to an end customer is obviously, loss of revenue. And then on a capacity, expense capacity addition standpoint, if you can reduce the losses, right, that kind of helps you delay, some of the upgrades you may have had to do, without that. Renewables you all talked about, and obviously renewables come in different forms. There is obviously commercial kind of utility scale, wind, utility scale, solar, and so on. But there's obviously also the distributed nature of the renewables, especially solar. And if you look at the different topics within renewables, the one that gets the most attention in kind of utility grid operation is kind of the distributed nature of some of these resources, where load and generation are kind of intermingled, right? Typically in the same feeder. So utilities need to think about things like anti-islanding, right, to make sure that the generators never island, along with the load, power quality, harmonics and such, and then also kind of monitoring, right, to have that awareness on, what is happening at the point where these resources are getting, connected to the grid. And then when you take a step back and say, okay, you have all these renewables, now you need to integrate it. And because of the intermittent nature of many of these renewables, depending on the time of the day and how the generation coincides with load, there may be times when the system cannot take all the energy. So the graph you see on the left is curtailments, right? Which essentially means that these are times when this generator could have produced power, but was not allowed to produce power because the system did not have capacity to take the power. So one solution, obviously, to mitigate that would be to add energy storage, whereby even if the grid cannot take the power, you can store it locally, and not lose the opportunity to generate power. And then when the grid is able to take the power at a later point in time, you could dispatch that energy. And then economics on this front has worked, favorably over the last many years. Namely, the cost of energy storage, right, has come down almost an order of magnitude in the last decade or so, which kind of helps adding, a lot more of the energy storage resources. Another topic is, as all of you know, electric vehicles, and that kind of has an additional factor, right, if you will, on the load side, because there is a lot of charging, right, that may be happening on a residential scale. But the utilities typically don't have visibility, direct visibility in terms of those individual chargers, right? So that means that from a planning perspective and operations, right, they have to make, some judgments. And even if you go outside where the charger is, to the edge of the grid, the areas which is owned by the utility, even there, the sensing may be sporadic, right? You may not have enough information for you to use on a real-time basis. Um, Obviously, elephant in the room in terms of the security threats, both on the physical side as well as the cyber side. So how do we make sure that there is the type of access control, either on an IT basis or on the physical side of things? And then to complicate things even more, things like ransomware, right? There have been, in the last year, multiple attacks on utilities whereby information is locked up, and there's obviously kind of the malware aspect of it. And just to round off, kind of the trends and challenges, um, I think the other topic to think about is kind of the demographics of the workforce, right? So over the last many years, the utility workforce has kind of transitioned with a lot of experienced utility engineers, choosing to retire, and a lot of new talent coming in, right? So what essentially that means is that the way the system is monitored, operated, the expectations, right, of the workforce, keeps changing, right, as new generations come in. So things like, more visual, right, ability to visualize the system, more, in a very simple manner, kind of, taking some of the consumer electronics and that side of user experience, to the utility world as well. So those are kind of some of the trends and challenges. Now there are multiple aspects to all of it, to optimizing and fixing these. But I think that the key thing to kind of notice is that uh, there used to be a lot of discussion confined just to the physical domain, so just the flow of power, right? So having more devices on the grid, or having transformers that are low loss, and a lot of aspects of that used to be kind of the primary areas of focus. But what you see over the last many years, as more sensors have come in, right, as more computing power has come in, as more optimized ways of analyzing and modeling have come in, the information domain is becoming equally important. And in fact, these, I would say, today are interdependent, right? The physical domain needs the information domain, and vice versa. To illustrate this, just I'll talk about a case that happened at a utility, I think about a year back, right? So this is the utility which has a lot of distributed energy, primarily solar. It was a summer afternoon, kind of a summer peak load, and the load was so high primarily because of the air conditioning loads, that the generation was not sufficient to meet the load. So the utility then started a kind of a load shedding protocol, right, where they were trying to shed some of the loads which had agreed to be shed in order to make uh, the the demand and the supply the same. But as they were doing it, it also ended up losing power, or removing power to one of these distributed solar farms. So then what happened is that the energy management system, if you will, of that farm went down, which essentially caused the utility not to have any visibility of that generation resource. The protocol was such that they had direct transfer trip. So typically, if there is a fault on our generation system, utility may decide to trip that system and take it off the grid. But since there was no awareness of what was happening, because the solar plant had lost its EMS system, utility by default did a fail-safe and it tripped that generation source. So now you can think, now the situation which started off as an imbalance of more demand than supply became even worse because now the supply is even less. You just took away, right, the energy source which could have supplied the load. So this is just to give a simple example of how that interdependency work, and the fact that as these systems grow, the information domain becomes as important or even more important than just the physical domain. So we'll now take a few minutes just to talk about this whole concept of automating the grid, right? Both on kind of centralized substation basis as well as on the distribution side. So to start with, if you think about a power grid, right? If you go from left to right, typically you have different sources of generation, whether it's the conventional traditional sources, such as gas turbine power plants or maybe nuclear. And then you may have, a lot of, kind of utility, large scale renewable farms, right? Like large wind farms. And then, these all, are, typically not necessarily close to where the demand is. So there are, transmission systems which take the energy, from the generation plants to where, to closer to where the large loads are. And these transmission systems essentially are stepping up and stepping down the voltage to allow transmission of power. So on both ends of this transmission system, you'll have substations, right, which have equipment such as transformers, bus bars, control systems, and then all the protections associated with that, right? So whether it's relays, breakers, switches, and so on. And then once it gets to the distribution substation, the opposite happens, which is stepping down the voltage and then distributing to individual loads all the way up to the last let's say residential load on the line. Now along with it, like we talked about, there are other distributed generation sources, everything from rooftop solar to small scale generation to solar generation to EV charging to battery energy storage, right? So that's kind of the, if you think about it, right, that's kind of the lay of the land as far as a typical power grid goes. And then if you think about where you are going to optimize, you will find that there are a lot of different points where you can start optimizing. But in terms of investments, you obviously always start with a place where you think you can get the biggest bang for the buck, and typically, that's the distribution substation. And then after you get to a certain scale of automating that, then you look at for example the distribution system and things down the line. So if you think about a kind of a substation automation, right? So there are a lot of different pieces of equipment in a substation that is being monitored. Now, everything does not have the same amount of priority in terms of data collection and communication and storage. So on one end, if you kind of think about transformers, right? So you typically monitor the transformers for its life. So it's like temperature monitoring, maybe the state of oil and so on. That's important, but that's not from a communication standpoint, does not have to be real time, right? Does not have to be in any urgency, if you will. On the other end of the spectrum, you may have things like bus transfer, right, where you are transferring load from one bus to the other, or it could be operation of breakers. So those are kind of directly tied into reliability or safety, and those actions must take place immediately, right? So the critical aspect is the architecture that you put in to automate the system needs to be able to discriminate and prioritize. So now I'll pause here and just ask a question in terms of, I think most of you are familiar with the communication systems that happen in the power grid. A lot of different protocols are used to exchange information between devices. So what protocols do you see mostly in your experience with the utilities either you work with or you interact with? Okay, good amount of sampling. I see that Modbus, seems like, kind of the top, what you're seeing the most. And then you're seeing some IEC 61850, DNP3, and very very less of Profibus, right? So it kind of matches. I would say in real life you see, at least in the US, DNP3 maybe, right, a little bit more, in terms of popularity, and IEC 61850 is obviously kind of starting to come up more. So we'll close this poll and kind of go to the start talking a little bit about what we are what in terms of the substation automation, right? What are some of the things we need to think about? So IEC 61850, as many of you know, is a protocol that is that originated in Europe, but getting more traction in North America as well. Essentially, the philosophy of the protocol is to divide your asset, in this case the substation, into kind of three levels, right? So at the bottom you have all the devices, so it's like things like breakers, PTs, VTs, measurement devices. And then in kind of the middle layer, you have primarily the IEDs, protection relays, and at the top level you have kind of the substation management, if you will, right? So this would be things like the communication that goes from let's say a merging unit, right? Which takes information from a PT or CT in terms of the current that is measured, and then it sends that information to a relay, and then the relay does obviously makes decision making. It may control it, the information is used to control the various devices in the bottom layer, and then that information is communicated back into the station level, right, where you may have a SCADA computer, and then that information goes even further, right, to a large area control center, or even to the cloud. So some terminology that you typically hear: SMV, which is kind of the measured value. So it's kind of taking the values of primarily current and voltage, right? Because most things on a power grid, can be derived, if you will, from, if you know the voltage, you know the current, you know the frequency, you derive things like phase angle, and you derive things like differentials of currents and rate of changes and so on. So the sample measured value is a standardized way of collecting data, digitized data, measurement data, and that data is sent into primarily the IEDs, typically protective relays, and those relays make a decision, and they send a command. The command is typically in the form of what you call a goose message. And this message is what is communicated across in terms of one relay, talking to other relay in terms of the different control actions they want to take, as well as depending on the system, going back all the way to the individual devices, right, to execute that action. And then lastly, you have the what you call the MMS, right, which are the status messages. So this is essentially letting all the relevant equipment all the way up to the SCADA system know, right, the status of various different devices in the system. Now, just like we talked about in the last slide, not all these data streams are urgent and important, right? So you need to have a prioritization, so to maintain a certain quality of service. And for example, goose messages in the IEC 61850 protocol will get the highest priority because those are expected to be typically some control action, versus an MMS may have a lower priority. And the way the architecture is, it's multicast, which means the information is spread across. Obviously, you can choose to make the information flow only between certain devices, right? You can approach it using techniques like IGMP snooping, but otherwise, as a default, the information is multicast, right? Sent to all the devices in the network. So now, if you look at how the evolution, right, of grid substation automation has happened. On the left side, you can kind of see kind of the traditional, right, pre automation type substations, right, where you have obviously the physical devices at the process level, connected, by essentially control cables. And then you have, typically serial communication going from, the protection relays, to the kind of the central level. What then happened in terms of that evolution is the communication, from the bay level, so from kind of the relays up to the SCADA system, uh, got transformed, right, into a digital kind of an Ethernet communication, for example, using 61850. But the communication from the device level to kind of the IEDs, still kind of remained, right, in kind of the analog world, if you will. And then if you what you would then call a fully digital substation is if all the communication, all the data acquisition is turned to be digital, which primarily means that the end user equipment, right, whether it's measuring equipment, whether it's protection equipment, needs to be able to be integrated into the digital network, right? So once that happens, then you can call that fully digital substation. IEC 61850, I think a lot of you mentioned Modbus as something that you see a lot in the systems today. Again, IEC 61850, use standardization, uses more descriptive, right, terminology, standard terminology to designate, right, the various, data points. The other thing to kind of think about if you are a grid operator or a system operator, right? The concept of redundant systems, right, whereby there are multiple ways that a certain signal can flow, is not really strange to you, because on the power flow side, if you just think about the electrical flow, most systems are laid out in a loop configuration, right? Which means that most customers have two paths of getting power. So they may have a primary substation they are connected to, and then there is a secondary substation. There may be a normally open switch, right? Where as long as the power is coming from the primary substation, you would not backfeed. But if the power fails from the primary substation, you would backfeed from the secondary substation. Same concept. So if you think about that on the communication side, you need to make sure that since communication is critical, there are multiple paths, right, to send signals, to the various different devices. So there are a couple of different protocols, right, that are typically used. One is called PRP, and again, the whole idea is that you are not reliant on one path, right, for your communication. So if you think about as an example, let's say you have a system where you have a substation computer, and then you have multiple switches, and this computer is trying to communicate, right? Send something to an end device. Rather than relying on just one local area network, you could choose to have two independent local area networks, and this SCADA system, as in this example, send the packet, duplicate the packet, and send it two different ways. You can send it through the green path as well as the orange path. And once the recipient gets that message, they know that the first message that comes in is all they need. And when the second message comes in through an alternate path, they can simply discard it. So this is critical again, not just for kind of fault mitigation, but also for maintenance, right? Sometimes you may have to take one of the networks out for maintenance, but you can still keep your substation running. Another protocol that is used is called HSR, right? So it's a high availability system redundancy protocol, and similar concept, but in this case you are thinking about a ring. So rather than using two different local area networks, you are essentially connecting. So in this example, if you look in the bottom, you can see there are for example, let's say there are multiple IEDs, and they are sending signals. So rather than send a signal only on one side of the ring, you can send that same signal both ways, right? And as the intended recipient sees the signal, the first signal, then there is no need for it to wait for that the second redundant signal. And in order to optimize the bandwidth, As soon as the signal completes, one loop, travels one loop, it obviously gets back to the sender, and the sender knows that that is the signal it sent, and it simply discards it. So these are kind of couple of different ways that whole concept of redundancy is maintained on the communication side as well. And when you think about equipment on the communication side, right, there are various different, right, all the way, if you think from the station level to the process level, right? So there are different types of switches that may be involved. There are different computing solutions. And the key thing is that, for, these protocols, to be able to be implemented, these devices, need to have, inherent capability, right, of duplicating packets and having these kind of dual nodes. On top of that, you can also make existing kind of legacy devices as part of these networks. Although they don't have the native capability themselves, you could use solutions like the redundancy box, whereby that the redundancy box now can allow a legacy device to participate, right, in some of these redundant communication solutions. And that kind of brings us to kind of the computing side, right? Because when you talk about communication, typically a lot of attention is given on the networking and the the switch and the router side. But computers, from a power system perspective, is equally important, right? Because as time progresses, you would end up seeing more and more virtualization, right, of devices. So rather than having distributed protection devices, over time, some of these functions will get migrated, to, for example, a central computer. So the computer needs to be able to participate in all these schemes, like we talked about the redundancy and so on, just like a switch would participate or a relay would participate. So all the kind of the key attributes, you would look at, needs to be, available for the computers as well. And that kind of talks about, purpose-built computing, right? So um, things like, the PRP protocol we talked about, or HSR, needs to be natively, right, available in these computers, as opposed to having to be, paired with additional switches and devices. And this kind of differentiate, right, this class of computing from the general purpose computers, which has, its place, but from a power system perspective, right, you would look at more dedicated, computing, solutions. Another important topic, as we think about connecting all the different devices, is the ability for all the devices to, look and agree on the timestamp. There is a lot of inventions and advancements that are happening, whereby you are going to ultimately look at a waveform level of information from various different nodes in a distribution system. So in order to really get to that next level of intelligence gathering, you may have to pull like microsecond type of data coming from different systems. So it's very important that all the systems have a common reference as to what the times are. One protocol that is used in power systems is called PTP. It's a precision time protocol, whereby you have a master clock, right, which has a master time, either coming from, let's say, a GPS synchronization, or it could be from some sort of a high fidelity atomic type clock. And then that time is sent across the system. Well, traditionally, when you send time signals, it's understood that there is latency in the system, but typically that's not a big deal, because the type of accuracies you are looking at maybe in the millisecond, right, or tens of milliseconds type of level. Versus today, now we are talking about microsecond or nanosecond type accuracy. So when you talk about that level of accuracy, you cannot simply take the time that has been sent, from a master, but you also need to correct to all the delays that happened as that time signal, traveled right through the network. So precision time protocol allows equipment that is certified for it can correct, can calculate, right, the latencies and correct those timestamps. such that it knows as the time reaches it, it's not the exact time that was sent by the master clock, but it's that time plus some latency. So it's high fidelity calculation. Again, the equipment that is used in the network to pass on the time signal, all of them need to be able to do these corrections on a hardware basis, right? To make it as quickly as possible, as opposed to the software CPU based, which adds additional latency. Protocol conversion is another topic, right? As you um, modernize substations, obviously you have substation has been built over a long period of time. There are a lot of legacy devices, and some of them, like you mentioned, may have been talking in different protocols, like Modbus or DNP3. How do we make sure that those devices can also become part of the system, right? So you need to be able to convert some of these protocols. For example, from DNP3 to 61850 as an example. And then the situational awareness piece of it, right? So there is a lot of equipment that is spread across. How do we make sure that there is an easy way, to look and understand, right, the type of devices and the communication schemes that are out there. So monitoring the devices, making sure that right, what each of the configurations are, what is the firmwares that are there, and then collect all the events and notifications. And then if you kind of think about kind of the next level, you can say, okay, so I got all this equipment. A lot of them may need maintenance, but I don't want an unplanned outage, right? I want to be able to monitor the equipment and then kind of look at kind of a periodic maintenance schedule. As an example, the fiber optic system, right? The fiber optic system may have been installed some years back. How do we constantly make sure that the system is still with operating with high integrity? So an example of this would be to look at the decibel levels, right, of transmit and receive, and then have rules where you have ways to flag that. Or if you think about kind of the redundant we just talked about, again, it's a complicated ways if you just think about setting it up. But an operator is not really an engineer, right? Who's typically not an engineer who's intimately doing the settings, right? So they need to have a easy visual way to see, okay, this is how the system is set up, and this is how the information is flowing. Now we'll take just a minute to talk about distribution automation, right? So far we have been talking on kind of the substation level. Now, if you think about going outside the substation, right? So there is millions of miles of distribution systems, a lot of devices out there. One of the schemes that are used by utilities is what you call CVR. Just going back to our initial challenges we talked about, how to reduce kind of the peak demand. This is a scheme which looks at voltages across the system and tries to optimize the voltage at the last point in order to manage the amount of power that needs to be sent. But this requires a very tight management of the voltage, because if you reduce the voltage too much, you could bump against regulatory issues, right? So you may be violating, as an example, ANSI standards. So you need to have a very good idea of what the voltage at the last node is, which means you need to be able to sense it, and you need to be able to send that information back into, for example, a SCADA system. Again, communication comes into play there. Fault location. The other aspect is typically when a fault happens in the grid, right? So the substation sees the high current, the breaker trips, but where exactly is the location of that fault? Takes typically some time to find. It may involve physical kind of scouting, right? So you have truck rolls going across, looking at various different things. You may have some models that you may have used, that may give some approximate solutions, or it may give multiple solutions, right? It may say the fault may be here, or there. Well, as time progresses, you see things like facial measurement units, right, that are being used to closely monitor, right, the waveforms, send that information, and use waveform recognition to have signatures and find that. Again, requires collecting these data securely and sending these back in a high low latency manner for the system to make decisions on where to send the crew or how to fix the fault. The other aspect is, there's a lot of devices which are already on the grid, right? So things like reclosers or capacitor banks or PTs and CTs. All this information, right, today may not necessarily be used in a central manner. It may be used kind of just locally. All that information, right, as the communication systems expand, the utility would want to see, right, all this data. So again, how do we make sure that all these the features we talked about on a substation, which is a contained system, those same systems are expanded right outside the substation, and the data is used. Same for environmental monitoring. Again, right, you could make a lot of decisions based on conductor temperatures, ambient temperatures, humidity levels, and so on, to make a more intelligent dispatch of power. And as utilities think about sending some of this information out from a distributed grid, many have been relying typically on public networks, such as commercially available LTE networks and so on. But as you are going to get to that next level of automation, you need to be able to have the confidence, right, that the information that is being sent is going to be sent with low latency, right, high resolution. So that may mean that you may need to own your own private LTE or private 5G type infrastructure. Now we'll get into renewable integration, and we'll just talk about battery energy storage, right, as an example. So if you think about a battery energy storage system, three main components, right? So you obviously have the batteries or the cells itself. Then you need to have a mechanism to convert all that energy, DC to AC, so a power conversion system. And then you need to be able to integrate all that into the grid, which is an energy management system. And busy slide here, but just to show that there is a lot of different pieces of information that needs to be collected, consolidated, and acted upon, for a seamless, integration of an energy storage. Not only does the storage have energy storage have demands on electric flow, but also has a lot of auxiliary systems, right? So things like air conditioning, fire suppression, and so on. All those need to be monitored. All those may be in different protocol formats, and all those needs to be consolidated and then kind of presented to the energy management system, which will make decisions on how to optimize the system, the state of charge, and then also how to respond, right, to commands coming from the grid. And you can kind of see, if you kind of take a deep dive, inside, if you open up a container, full of electric batteries, right, kind of the BESS container, you can kind of see the amount of demand that is there, right? So there is demand for kind of low cost computing, whereby you're measuring individual parameters and making kind of local decisions. You are collecting a lot of analog data, converting that into digital. So it could be from an air conditioning system, it could be from a fire suppression system, a UPS, and then you need to securely pass all this information from a networking standpoint down to the PCS and the EMS. And then you have to keep doing it in scale, right? Because most of the energy storage systems will have multiple banks of batteries. So if you have to repeat the setup every time you do it, that's really not the best use of time, right? So you need to have tools and devices that can help things like fast configuration, right? So automatically detect the devices that are in the system, automatically assign IP addresses, and then have kind of the switching and routing that is expandable, right? So when you had the next block, right, you have enough capacity to expand. Same for commercial kind of the solar systems, right? So if you have same type of topology you can think about, right? There's measurement, there is inverters, then you are sharing information between between the inverters to maximize your power flow, minimize the losses, and also you're presenting data to the grid operator. So hopefully you see among all this, whether we talk about substation, energy storage, solar, all of them have a common thread, which is that you need to have equipment, right, that is designed to all these different functions, if you will, because the functions are related to the same. You're collecting data, digitizing it, monitoring it, helping to protect it, and then taking all that information and redundantly sending back to the grid. And same goes with small scale, right? So now if you kind of step back and say about not the integration, but the individual type of prosumer, if you will, right? And they're also kind of similar needs, but the difference here would be the 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 person who owns this kind of a very small distributed energy, for example, a rooftop system, you don't have the SCADA system, right? So you're not relying on any utility communication. So you need to have the ability to use IoT type, right? So IP-based communication. So things like IEEE 2030.5. And similar concept on EV charging, right? So you could have systems where there is electric vehicles paired with solar systems with energy storage with the grid. Again, similar type of information needs to be exchanged. And how do we make sure that the building blocks you use, right, are similar to what is used in rest of the grid to improve. Same can be said about EV charging stations, right? So multiple banks of EV chargers. There are power panels. There are low voltage breakers. All these to be monitored, and not only the electrical parameters, but even kind of some of the service parameters, right? Because most of these will have a collection system, for from a monetary standpoint. So you need to have systems that are able to collect both technical electrical information as well as the service level information. On the cybersecurity side, right? So all this needs to be done in a secure manner, and cybersecurity means there are multiple layers, right? So you need to think about as starting with at the device, then the network and the management. So at the device level, you need to make sure that the devices that you're using are certified, right? So for example, IEC 62443 is a standard that is generally used. So did the design of that, that whole design process, did it go through, right, that certified process? Does it meet all those requirements? Then at the network level, you need to think about, okay, what are the different, segmentation strategies that you need to use, right? So if there's an attack, is there a way for you to segment and localize, right, some of these components? And then at the management level, right, how do you have the policies, the firewalls, right, implement security policies, making sure that you're able to monitor these devices, make sure that they are upgraded, they're on time, and so on. And then kind of thinking about the NERC-CIP side of the requirements, right? Again, NERC-CIP is a collaboration, right, between the asset owner and kind of all the device providers. So the device providers, support the asset owner, by making it easier, by making it, more, apparent, right, in terms of the various different requirements and various different tools that the asset owner can use, to implement the security policies, right? So, for example, in some cases, it may be a particular device that may allow you to do an electronic security, perimeter, like a SIP 05 would say. In some other cases, it may be an HMI, right, a GUI that will help you, to do that, overall monitoring. You also need to be able to, from a visibility perspective, look at the various different devices, and then look at what level of security, right? Because each of them may be assigned different levels of security, and are they capable, right? Are they at the right level of security? And then what changes do you need to make in order to get them to the desired level? You look at kind of intrusion detection, right? So we talked about like goose messages in the beginning as a critical piece of message. How do you make sure that only legitimate messages are going, right? So is there a message that is coming from maybe a device that is not part of your network? So you need to be able to do, pattern recognition. You need to look at, timeout events, and then, make enough alarms so that the grid operator is alerted, right, that this event is happening. Or it may be, kind of doing a map of all the equipment that is out there, right? So all the IEDs out there. So we started with a base list. Okay, these are the IEDs I expect. The system does scan and it finds something else, right? So is there an unauthorized device that's out there? You need to be able to back up and restore, right? So the configurations need to be controlled. Obviously, that's a SIP requirement, NERC SIP requirement, where the configurations are obviously revision controlled, and they are kind of backed up, right, in a system where if something happens to a particular device, right, you can take that the previous configuration and apply it. Similarly, firmware management, right? How do we make sure with thousands of devices in your system, how do we make sure that each of them are at the latest level of firmware? Again, requires the ability to do that overall system view that allows you to consolidate all this information. And then last but not least, kind of the hardware security, right? So there is a lot of ways malicious actors can impact the hardware, right? So how do you make sure, for example, things like disabling USB ports and having critical USB information or port information directly inside the hardware, right, as opposed to externally accessible. Having the type of secure boot that you may need, right, or TPMs, right, to secure the hard drive, and even physical kind of protections against inadvertently turning off or resetting devices. So that was a quick look at kind of the different strategies you may use, and I would end with a few thoughts on if you think about, right, the different partners you can work with, some of the key attributes, right, you would want to look at. The first thing I would say is kind of that application expertise, right? So it's one thing to know about the products, right? But the more important thing is uh, have that understanding on applying the products, right? So what is the experience that the partner has with working on creating new architectures, right? Or adapting products, or what are their level of commitment, right, in terms of contributing to the standards, right? So I'll summarize as kind of the solutions mindset. Second is, like we talked about, there is a lot of piece of equipment, that comes into, play here. And many of them, need to be kind of purpose built, right? So which means that the devices, right, have actually, gone through the capability of kind of that native, right, native inbuilt ability to, participate. The robustness of the product, right? So typically harsh environments, how do you make sure that the product, can survive, right? So what type of, backing does the manufacturer have, right? So what is kind of the, let's say, the MTBF of these products? What type of testing has happened? And then, lastly, I would say, ease of use, right? Ease of use is essentially how easy is it to commission, to maintain, how easy is to troubleshoot, how easy is to get, ongoing support, right? So those are some of the key, criteria, that we can kind of, think about. So at this point in time, we'll kind of pause. We'll have a little bit of time to take some, questions. As you have all patiently, taken the, time to listen to this presentation.
Hey, thanks, Kuru. This was all very informative. That's awesome. We just have one more poll question for our audience at the end here, which I will go ahead and put up on your screen. Let us know if you'd like us to connect you with the Moxa expert to discuss any projects that you may have. I'll just keep this up here on your screens for just a minute as we start our Q&A session. If you'd like to submit any questions, please use that Q&A function in Zoom, and we'll do our best to get to it here. We do have a question here, Kuru. Why don't I read this off for you?
Yep.
And how is MX View 1 with power module licensed? Is it by node, or by package?
Yeah. So a good question. So, just to explain to the audience, power module, right, is kind of just an add-on, to the MXV1. It kind of, brings up, some of the, power grid specific, right? Things like PRPHSR, visualization, PTP, and those types of, functionality, right? So yeah, so these are perpetual licenses the way we do it. It's not an annual license. And we can license it by the node, right? And again, it's a perpetual license. Same for MX security. This is again an additional capability in terms of the visibility we just talked about, looking at the different IEC levels and so on. Again, right, can be licensed on a node basis. It's kind of again in perpetuity.
Okay. Here's another one. What type of processors do you use in the computers, and do the computers support time synchronization?
Yes. So processors, yeah. So we have multiple versions. I'll just talk about the DA820C, which is kind of the substation computing. So we have the Xeon, Intel, Xeon based processors, as well as the core, right? i5, i7. Those processors are all supported. The other question on the PTP, yes. So the substation computers do have native PTP support, which essentially means that it's done on a hardware basis, uh, which is even another level of latency reduction compared to kind of a software-based, doing PTP. So you're essentially removing that CPU and all the demands that may be on the CPU that could potentially delay, this the time stamping. So yes, the DA20C native PTP does not have to use any other equipment, to be part of the system.
Okay, so speaking of computers, let me just jump to this question. Do your computers support running virtual machines?
Yes. So we do support virtualization. Has been tested, with products like VMware. And again, right, we see many substation users using virtualization because again, right, you may have different, you may have Linux running, you may have Windows running, and so on.
Thanks, Guru. Um, Here's another question. You mentioned IEC 61850 capability. Is this available at the station bus level only, or is it available at the process bus also?
So it's available at both levels. So meaning, so just to explain, process buses, it's the communication, between the device level. So, things like, let's say a merging unit or a circuit breaker to the relay, right? So that communication is, typically considered process bus. So yes, so as long as there is digitized signal that is available, like for example, a merging unit converting a PT or CT signals, in a digitized format, the same devices that can be used at the station level, right? So the same switches, same routers, can be used at the process bus as well. And moreover, we talked about redundancy. So it's kind of HSR, type ring topology we talked about. That's typically, used in the process bus level. So the devices we are talking about are, capable of, doing that as well.
Okay. And we're coming up at the hour, so I think maybe we have time for just one more question here. Um, Amount of power available may be limited in some situations, like with remote devices on distribution. How much power do your switches consume?
Oh yeah, so it's that's a generic question. I would say a switch without a PoE, right? So meaning the power just for operating the switch, typically, it's in the, I would say, the 10 to 15 watt range. But as we go kind of on the distribution side, so you have products that are available, which are which are at the few watts type of level, right? So typically, I would say substation level, assume 10 to 15 watts. Typically not a limitation because substation has enough power. As you go into the distribution side, there may be places where the power is really limited in terms of the PT supply and so on. So there are products available in the few watts range.
Right. Awesome. All right, everyone. Thank you all for joining today's webinar. We will be sending a follow-up email with a link to the recording so that you can revisit any of the topics that we covered here again. A survey will appear at the end of this session. We would appreciate it if you could give us your feedback on how the webinar went. And lastly, thank you, Kuru, for sharing your experience and your expertise on secure and reliable networking for smart grids. This wraps up our webinar. Thank you everyone for attending, and we hope that you found this information valuable. Have a good one.
Thank you.